So, can quantum computing actually replace classical algorithms? Let's dive right into this explainer and unpack the massive hype we're seeing right now. If you follow the tech space even a little bit, you've probably heard some absolutely wild claims. But are our classical computers, like the laptop sitting right in front of you, really about to become totally obsolete?
Right. Is classical computing literally dead? Well, to figure that out, we really need to look past all the fleshy buzzwords and understand exactly what these futuristic machines are promising to do, and, maybe more importantly, what's actually holding them back.
So let's get into section 1, the quantum promise, breaking boundaries.
Look, quantum computers aren't just faster processors. They're an entirely different paradigm. The two massive promises here are that a large-scale quantum machine could completely shatter widely used encryption schemes, basically the stuff keeping the internet secure today, while simultaneously allowing us to perform exponential physical simulations. We're talking about opening up completely new frontiers in science.
But to wrap our heads around that kind of mind-bending speed, we need to move to section 2, bits versus qubits. We literally have to unlearn classical computing.
Okay, so a classical bit is strictly a binary state. It exists as either a 0 or a 1. Think of a light switch. It's either on or it's off. But a quantum qubit, it exists in a linear combination of states simultaneously. It's kind of like a coin spinning in the air. It's not heads or tails yet, it's just a blur of both at the exact same time.
This brings us to the absolutely crucial concept of superposition. That's a quantum state where a qubit exists in a linear combination of states before it is measured. It's the absolute backbone of how these new algorithms function. The information isn't locked into a definite 0 or 1 until the very second we measure it.
So, how do quantum algorithms actually work? Well, step 1, you manipulate the qubit in a very particular way. Step 2, you amplify the probability via wave interference. Think of ripples in a pond perfectly combining to make a much bigger wave. And step 3, you measure the final state using a probabilistic rule. It's not simple linear math. It's an entirely different way of coaxing out the exact answer we need. Which leads us to a massive roadblock. Section 3, the noise problem. Time for a hardware reality check. If this is so incredibly powerful, why aren't we all carrying quantum smartphones? It boils down to quantum decoherence. This is the loss of a quantum state when a qubit isn't perfectly isolated, which introduces fatal noise and error into the calculations. Basically, these states are incredibly fragile. A tiny bit of environmental noise, and the whole calculation is completely ruined. To fight this noise, the hardware setups have to be extreme. Some systems use superconductors, which isolate an electrical current by entirely eliminating electrical resistance. Others use ion traps to confine a single atomic particle using incredibly powerful electromagnetic fields. So yeah, these are definitely not machines you can just toss in your backpack.
Because of those physical hurdles, here's section 4, milestones, not deployment. Let's look at where we actually stand in 2026.
You've probably seen the bold headlines about quantum supremacy. That's a specific metric where a quantum device successfully outperforms a classical computer on one specific task. But here is the critical takeaway. These demonstrations are purely scientific milestones, not evidence for near-term real-world deployment. The specific tasks they're winning at aren't actually useful yet. They just prove the physics works. So for now, your classical laptop is totally safe.
But things are moving fast. Section 5, the $10 billion bet. The race is officially on. Despite the incredibly sobering reality of noise and decoherence, governments are racing to figure this out. Global government investment in quantum computing hit a staggering $10 billion by April 2025. That's how high the stakes are. Everyone is desperately trying to engineer qubits with longer coherence times and lower error rates.
So what does this all mean for us? Will quantum computing crack the code before the noise stops it? The big question isn't really whether they'll replace classical algorithms tomorrow. It's whether we can engineer our way out of this noise problem before that massive global investment runs dry. That is the multi-billion-dollar question defining our next technological era. Thanks for joining me on this explainer, and definitely keep your eyes on this space.